Well, first of all, I want to take the opportunity to thank all of you for being so welcoming of me to IAS. It's been a really smooth transition from Illinois, and it's been awesome to get to know so many of you, and I look forward to continue to working with you all. So as Jim already pointed out, I'm trying to keep things in the spirit of Halloween. This is the last seminar before Halloween. And I've tried to make this little slide here for you, and I thought maybe I could try and tell you a little bit of a spooky story to start things off. And that is something that I don't think a lot of you appreciate about the fields that you are in. So a lot of you, I think, are studying some of the most distant objects in the universe, or some things that are not quite as tangible as the moon. And one of the pleasures of studying the moon is that when you are in the middle of the cornfields in Champaign, Illinois, and it is about your thesis time, you're supposed to be finishing up your work, there's something bad that happens. When it is quiet outside, middle of the night, sometimes there's a looming full moon looking over you. And if you're quiet and there's not too much rustling in the cornfields, you can almost hear it say, "Patrick, shouldn't you be working on your thesis?" Yeah, so a lot of you were probably surprised that you heard that I was from Charles Gamey's group, but am not working on black holes. But Charles is credited with saying he thinks that anybody who thinks that black holes are interesting will also find moon formation interesting. So let's dive in. So the leading theory for the formation of the moon suggests that nearly 4.5 billion years ago, during the final stages of terrestrial planet formation, a planetary impactor struck the proto-Earth in an off-centered collision. This collision produces liquid and vaporized rock and launches it into orbits around the proto-Earth, forming a protolunar disk. It is from this protolunar disk that we think the moon ultimately coalesced. Any moon formation theory must explain three observables. First is the current Earth and lunar masses. Second is the present angular momentum of the Earth-Moon system. And finally is the lunar composition. So again, unlike many other astrophysical systems, we've actually had the unique opportunity to visit the moon and collect samples. As it turns out, geochemical analyses of lunar rock provide key insights into the moon's origin. So one particular and famous geochemical diagnostic of lunar samples compares lunar oxygen isotope ratios to terrestrial oxygen isotope ratios. So in this figure, I'm plotting something that maybe many of you have never seen before, and it's a little bit of a weird plot, so let me walk you through it. The Earth and lunar delta oxygen 17 to delta oxygen 18 isotope ratio is plotted, where delta oxygen M is dependent on the ratio of oxygen M to oxygen 16. For planetary bodies, this ratio will typically fall atop what is called a mass-dependent fractionation line with a slope of about a half. But again, why plot this weird quantity? Well, albeit most planetary bodies do have isotope ratios that do fall atop this mass-dependent fractionation line with slopes of a half. Many planetary bodies have fractionation lines offset from the terrestrial fractionation line, which I've here shown as TFL. This offset is a reflection of each planetary body being derived from different material reservoirs. So in a way, these ratios act as a barcode, or a DNA, if you will, for a planetary body.
That's the situation.
Yes.
So yesterday I was talking with Stanislas in biology. He was telling me that presence of lots of oxygen in rocks on Earth is a consequence of having life on Earth. And the moon, as far as I remember, didn't have life. Can it be somehow explained through that?
So I don't think that these ratios are, I think that the mass-dependent nature of these processes could be influenced by life. For example, photosynthesis, as it operates, will act to fractionate isotopes in mass-dependent ways. But I think that even other processes that are non-biological will also contribute to this mass-dependent fractionation. And so I don't know if this statement is as relevant to these samples.
This would be a planetary average value, though, correct?
So each one of these data points that you see represent a single sample,
Okay.
which are derived from either a meteorite or a terrestrial sample. Okay, so back to why this is a little bit weird. Martian meteorites reveal that Mars is offset from the terrestrial fractionation line. Mars's DNA is different than Earth's DNA, as expected. Now, lunar oxygen isotopes fall almost directly atop the terrestrial fractionation line to within measurement uncertainties. In other words, the Earth-Moon system are more similar in oxygen isotope ratios than any other two measured bodies in the solar system. But in the giant impact hypothesis, a Mars-sized impactor is invoked to strike the proto-Earth and produce a disk of debris. So shouldn't we see a trace of the impactor in lunar samples? Well, how can we explain it? The first way of going about explaining this is that perhaps the impactor was isotopically identical to the Earth. But this seems unlikely given the diversity of oxygen isotope ratio measurements of meteorites and from other bodies in the solar system. The second way of going about explaining it is saying that material was vigorously mixed in the impact or the evolution of the protolunar disk, such that this mixing could erase the trace of these isotopes. The erase is such that we see that the moon and the Earth have similar isotope ratios. And yes?
Is this can only be done for oxygen, or there are other elements that you can do?
There are other isotopic systems that this has been observed in, including potassium, silicon, titanium, and tungsten, famously.
If the lines for other solar system bodies deviate more than the Martian line or similar to the Martian line?
Yeah, great question. So in this plot, we see that for a given delta 18 ratio, we notice that Mars samples are enriched in oxygen 17. And there's been something that suggests that perhaps this ratio changes linearly with heliocentric distance. But if you were to plot meteorites from Vesta, you would find that they actually fall below the terrestrial fractionation line. All right, so I gave you two possible explanations: mixing, maybe they were the impactor was isotopically identical, but perhaps the third explanation is that the giant impact hypothesis is just flat out wrong. All right, so moving forward, to seek initial conditions for a giant impact scenario that produces a protolunar disk capable of forming our moon while simultaneously explaining these three key observables, a large simulation effort began in the 1980s with the pioneering calculations of Benz et al. In 1987. And there they performed smooth particle hydrodynamics calculations of the giant impact using about 2,000 particles. Flash forward to today, Kagaris et al. 2020, which is shown in the bottom right panel, is boasts the use of 10 to the 8 SPH particles. So it's worth noting that most numerical simulations of the canonical giant impact have debris disks that are formed from at most 30% of Earth-derived material. The remainder comes from the impactor. Hence, you're only pouring gas atop the fire that is the isotope crisis. Some simulations have identified more mixing due to the impact, but a lot of these rely on inventing scenarios to relax the angular momentum constraint on moon formation. In other words, a lot of these models invoke a high angular momentum impact such that the collision itself easily mixes material between the impactor and the proto-Earth. A few more interesting notes. To date, very few calculations have been performed with a grid-based algorithm, except for Wada et al. 2004, which used the Zeus code, Canup et al. 2013, which used a lab-based CTH code out of Sandia National Labs, and finally, my recent work from this year, which is shown in the very, very bottom right corner. But the major motivation for my work, and the thing that I want to talk to you most about today, is that no giant impact calculation has considered the potential dynamical role of magnetic fields. So let's, yes.
Ask one more basic question about what do we know about the impactor? Do we know where it formed, what composition it had, or what would you put in if you say that at the end of the day, either the composition is wiped out or not?
So your question is, where did Theia come from?
Exactly.
Okay, yeah, so this is actively debated. So there is a paper by Belbruno and Gott that suggested that that Theia stably formed at Earth's L4 or L5 Lagrange points. And because of that, they may have been derived from similar material reservoirs such that they were, this idea of the impactor being isotopically identical to the Earth is not a bad one. But people have followed up this idea with n-body simulations and find that these points are so stable that they can't actually find a way to excite these impactors out of these Lagrange points that actually impact the Earth. Some suggest that Theia comes from the inner solar system. Others suggest that Theia may have even come from the outer solar system and might have been one of the ways that we deliver water to the Earth. So this is actively debated.
Is there general agreement amongst this sort of library of simulations where there is a certain impact parameter, mass ratio that forms the moon, regardless of which code you use, regardless of what resolution you use, that there's a robust mechanism that we all agree upon works, and now we just need to add more physics to understand it, or all these just totally different parameter values that may or may not form the moon each time?
Great question, Jim, but I think you're asking like 5 different questions there. So first let me tackle one, in that there is a canonical giant impact hypothesis, which invokes a collision on a zero energy parabolic orbit between a 0.9, I think it's, let's see, a 0.9 Earth mass proto-Earth and a 0. Actually, I need to check on the mass ratio, but there's a known mass ratio and a known impact velocity that is corresponding to the canonical giant impact hypothesis, which is known to produce a protolunar disk that is at most several lunar masses and is consistent with the angular momentum constraint on moon formation. With that being said, these canonical giant impact models are the ones that I have suggested have produced these disks that are mostly derived from impactor derived material. That's why a lot of people have been looking at these higher angular momentum impacts, where the initial impact angular momentum is like 2 times the current angular momentum of the Earth moon system. Your second question is, do different people agree, given a canonical giant impact hypothesis where we think that this is going to produce the correct observables, do different models agree? And I think another interesting question to tackle onto that is, do grid-based calculations agree with SPH-based calculations? So one of the panels that I've shown for you here in the middle, Canup et al. 2013 used a CTH code, used the CTH code out of Sandia National Labs and found generally good agreement between those models and those using SPH-derived methods. On the other hand, Wada et al. 2004 top panel used the Zeus code, and they did use a different prescription for the equation of state for these materials, but they found that spiral shocks in their simulations were so efficient at transporting angular momentum that all of the disks fell onto the object, and therefore what they saw was not a possibility for replicating the moon as we see it today.
Probably just Zeus, it's wrong.
Yes.
So you mentioned that these simulations need to explain the 3 observables like mass, angular momentum, and composition. Then how about the orbital alignments between moon and the Earth? Is that an important observable?
Yes, it is. So also being able to explain the current inclination. But a lot of these are coupled to taking the outcome of impact simulations and then tracing out to where the moon actually forms, and then looking at the orbital dynamics of that system. So I think that coupling these two is still something that's actively being worked on in the field. Yes.
Maybe one more question before you move on. What do we know about the time scale? This tells you what disk you get, but I guess you cannot track it to the point where it actually forms the moon.
That's right.
Know about the time in between.
That's right. So a lot of what I'm going to be talking to you about today will be timescales for the formation of the moon. But generally, what is expected is that if you were to assume that the disk was completely solid. There are these calculations by Ida that show that the moon forms within a few months, but these after the giant impact. But those have been shown to not be exactly correct, because really what you need to be doing is be considering when material is pushed beyond the Roche radius, which is dependent on the amount of angular momentum transport in the disk. And so other n-body simulations have prescribed a way, I think this is Salmon and Canna, have looked at injecting n-body particles beyond the Roche radius at a rate determined by what angular momentum transport they expect in the interior of the disk. And they find that the moon actually forms thousands of years after the impact. So of course, if the 1,000 years is the time you have to look at, there's no way a calculation like this will actually be able to integrate that far forward. In fact, as far as I know, the calculations which I'll be showing you today push this to about 10 days post-impact, and those are the longest integrations that I'm aware of today. Okay, I am behind. Okay, so question I wanted to ask today is, how about magnetic fields? So let's first talk about what are the potential sources of a magnetic field. So it's possible that the impactor and or the proto-Earth hosted a magnetic field prior to the impact. All solar systems, with the potential exception of Venus, either hosted or presently host a magnetic field. The ancient magnetic field of the Earth is not yet well characterized. There is some evidence for a field hosted by the Earth as much as 4.2 billion years ago, but these findings are heavily disputed. And even if the proto-Earth and impactor did not host their own magnetic field prior to the impact, meteoritic data suggests that a background solar magnetic field strength of about 0.05 to 0.5 Gauss permeated the terrestrial planet forming region. This comes from measurements by Fluid all 2014. More recently, work from this month, Borlina et al. Similarly find field strengths of about a little bit larger than a Gauss for outer terrestrial, in the outer solar system. Okay, so those are the possible sources of magnetic fields. Now another question is, how could a magnetic field be amplified in strength to the point where it becomes dynamically important in the protolunar disk? Well, first, turbulence is capable of growing field strengths exponentially in time. However, often turbulent amplification is difficult to numerically resolve. In the context of neutron star mergers, Kyuchi et al., forget the year, found that they were actually able to amplify magnetic field strengths by many orders of magnitudes in this initial merging phase of the neutron star calculations. And they found that the amplification was unconverged in their calculations. Second, the debris disk that forms post-impact is nearly Keplerian, and it is therefore differentially rotating. Differential rotation winds radial field following the prescription, which I've shown you in the first equation here. So winding of radial field BR grows the toroidal field B phi linearly in time, and where here R is disk radius and T is time. So for plausible initial field strengths, magnetic winding alone could bring the field to dynamically interesting strengths within a few months. Third, differentially rotating magnetized flows can be unstable to the magnetorotational instability. The MRI is capable of growing field strengths exponentially in time with a maximum growth rate equal to 3/4 the Keplerian frequency, where I've assumed a Keplerian disk here. The MRI sources vigorous turbulence and angular momentum in astrophysical disks. So the top animation here shows a shearing box simulation where a 3D patch and a Keplerian disk is tracked using a co-rotating frame of reference at a fixed radius. And we can see that in this particular calculation, the initial field is completely toroidal. And as the MRI settles in, magnetized turbulence also settles in, growing field strengths exponentially. And in this calculation, magnetic field strengths were grown exponentially in time. All right, well, all of this would be completely irrelevant if I didn't talk about coupling. So is the magnetic field well coupled to the flow? Well, before I arrived at the University of Illinois and began my thesis work, Charles, along with Dr. Wei-Ting Liao and Dr. Paul Ricker, computed an estimate for the magnetic Reynolds number in the protolunar disk. The magnetic Reynolds number is equal to the sound speed multiplying the disk scale height divided by the magnetic diffusivity. And when the magnetic Reynolds number is much, much greater than 1, the flow is said to be well coupled to the field. So these two figures show that the protolunar disk is well coupled in hot vapor, where here, this Gammy-Leon-Ricker paper assumed a lunar rock composition for the protolunar disk. And they find that for temperatures above 3,500 Kelvin, at a disk radii of 2 and 4 Earth radii in the protolunar disk, that there you are well coupled to the field. And this is largely attributed to thermal ionization of sodium and potassium. So where may the field be not so well coupled? Well, there may be weak coupling in the interior of the proto-Earth, at the surface or high elevations in the protolunar disk, or at large disk radii. All right, well, let's consider the scenario that hot vapor.
Can I ask a question?
Yes.
I'm on Zoom. This is Romain Tessier. I'm in Princeton right now. The question I have is to define the magnetic Reynolds number. Don't you want to use in the context of turbulent motion or rotational motion the turbulent velocity dispersion instead of the sound speed? And since if you have very subsonic flows, then the Reynolds number drops a lot.
So your question is, for the typical velocity, why am I using the sound speed instead of like a turbulent velocity?
Or some flow, some typical dynamical flow velocity instead of the sound speed, which is the hydrostatic the speed.
That's a good question. I will say that that different estimates for looking at coupling to the field instead look at the I forget the pronunciation, Elseiser number, which used for the typical velocity scale the Alfvén velocity. And they find similar agreements in finding that the protolunar disk is coupled for this parameter space for temperatures are greater than 3,500 Kelvin. So that's the best answer I can provide. Jim's raising his hand.
Well, I don't think you want to use the flow velocity directly, because otherwise in a stationary medium, you would say the Reynolds number is always 0, which is clearly not true. So in a fully saturated state, the RMS velocity dispersion is, of order of the sound speed, and maybe 1/10 of the sound speed for weak MRI turbulence. So I think that you're right, there's a factor of order unity that might be in front here, but it would be orders of magnitude smaller if you use the turbulent RMS Mach number for the MRI.
Yeah, but inside stellar interiors or planetary interiors, I'm not talking about impact. Impact, you have very large velocities, so you're right, what you say is correct. But inside planetary interiors, when you're in stable kind of hydrostatic configuration, you may have convective motions, which are really, really subsonic. And in this case, the turbulence is like 10 to minus 6 sound speed, or 10 to minus 5. But for giant impact calculations, the turbulence is probably transsonic or weakly,
Right.
Yeah. But my point is that you really need to compare to the flow speed instead of the sound speed. And the flow speed can be comparable to the sound speed. Then what you did is correct. Right?
So I want to go back to your point about the turbulence being, you were trying to distinguish the turbulence from the giant impact and the turbulence in the disk. But what we're working towards in this description is showing that the magnetorotational instability might be operating in the protolunar disk. And there, the source of the turbulence is magnetized turbulence, not turbulence from injected only from the impact.
Yeah, no, I agree. But I think the key argument is that the turbulence has to be transsonic or the Mach number has to be not too small. Right? Otherwise, the Reynolds number is not the correct one. That's just my point.
Well, this is a good question, something I haven't thought about. I'll try and get back to you, okay? Yes.
Just like where exactly are we on the spot in terms of temperature?
What is what?
In terms of temperature, are we hot enough?
In the protolunar disk? Again, really depends. So in the models that I'm going to be showing you today, they're going to be the so-called hit and run models, which are high angular momentum models, which are known to produce temperatures as high as 10,000 Kelvin in the protolunar disk. Okay, so moving forward, I wanted to give you some estimates for timescales. So let's consider the case that hot vapor is indeed coupled to the field in the protolunar disk, but other parameter space may not be. Turbulence heats the disk with a heating rate proportional to the inverse of alpha, where alpha is the familiar Shakir-Sanayev dimensionless measure of angular momentum transport. For an alpha of 10 to the minus 2, which could be realized through MRI-driven turbulence, the heating time scale is on the order of 60 hours. So the protolunar disk is comprised of vapor lunar rock, which has an extremely large opacity. So as computed in Gamma-Liao-Ricker 2016, the cooling time scale must be extremely long for the protolunar disk due to these large opacities. Therefore, cooling is inefficient in the disk, and because of the short heating time scale, it is likely that the disk may undergo runaway heating. And as we undergo runaway heating, coupling to the magnetic field becomes better and better. All right, so finally, almost out of the introduction. So the questions that I want to ask in this talk are, what is the outcome of a magnetized moon-forming giant impact? Second, could a weak magnetic field be amplified enough to become dynamically important in the protolunar disk? And finally, what are the implications of magnetic fields on the formation of the moon? All right, well, to answer all of these questions, we need to apply numerical simulations. So I'm a contributor to the Athena++ magnetohydrodynamics framework, which is code that is developed originally at Princeton University, but has roots in Athena, but also has been carried over to development here at the IAS. And using Athena++, we have developed the first numerical models of a magnetized moon-forming giant impact scenario. So our models solve the equations of 3D ideal MHD subject to self-gravity. And for self-gravity, we employ the open boundary condition Poisson solver from SciUp Moon from Seoul National University. And in conjunction with this open boundary condition solver, we use a special discretization of the momentum and total energy gravity source terms that recently appeared in an original paper in collaboration with Professor Tomoyuki Hinawa from Chiba University. Well, if you had a careful ear going back to the first item here, you might have noticed that we do not consider finite resistivity in this first set of simulations, which may not be a great assumption in some regions of the protolunar disk. As I'll motivate later, we do look at a particular class of model which is known to produce a very hot protolunar disk, bettering our assumption, but really we should be including finite resistivity in these models. Finally, in addition to MHD and self-gravity, we are not dealing with ideal gases in this calculation. We must work with an equation of state modeling liquid and vaporized granite. So what does that look like? Well, this is the Tillotson equation of state for granite. And this is the equation of state that we use in our simulations. So let me walk you through this plot. On the z-axis is the logarithm of the pressure. On the x-axis is the logarithm of the density. And on the y-axis is the log of the specific internal energy. All axes are, again, in logarithmic units. So if I were to plot an ideal gas in this 3D volume, it would plot on a single plane. The Tillotson equation of state is certainly not that. The Tillotson equation of state is analytic and broken into 4 regions. Perhaps the closest analog to ideal gases are the expanded hot states. And this is in region 4, which is shown in red. And this is at high temperatures and lower densities. Here, the equation of state is nearly planar. Contrast that with region 1 and the condensed states, which is given in orange. Here, the equation of state is quite stiff, where large changes in pressure are required for small changes in the density. Third is the green region, the intermediate state in the middle. And this part of the equation of state is merely an interpolation between the condensed states and the expanded hot states. This part of the equation of state is under some scrutiny by experts in the field because this interpolation region does not do a good job at all modeling this coexistence of liquid and vapor. In fact, a lot of leaders in the field have suggested that we move to tabular equations of state, which do a better job of modeling this part of parameter space. Finally is region T2, the expanded cold states shown in blue, where the analytic prescription for the equation of state gives negative pressures and imaginary sound speeds. So for here, we have to put a floor because we do not permit this in our numerical evolution. In the interest of time, I'm going to, I'll show this. So one of the questions that I'm frequently asked is, how do you know that after you've included an equation of state, how do you know if it's working? Well, one way of going about testing that is by doing the so-called shock tube problems. So if you have any experience in working with fluid dynamics, this is probably one of the first problems that you ever ran. And we are doing these same kind of problems, but now with a new equation of states. And for this particular slide, I'm showing you a shock tube that is carried out in the condensed states of the Tilson equation state. And luckily, from work from Coleman et al., or sorry, Chen et al., which also includes work from former member here, Matt Coleman, we were able to compare our numerical solutions to an exact solution for this problem for the Tilson equation of states. And here I'm showing you the Athena ++ solutions in comparison to the exact solutions where we're in excellent agreement. Something interesting is that another author in the field, Hasono, actually produced these results for their shock tubes using an SPH code. And I've also plotted their results here for comparison. And we are generally in good agreement. Okay, so now let's move forward to the impact calculations. So for this work, we performed several calculations employing a Cartesian mesh resolved by 256 cube zones and 512 cube zones corresponding to linear resolutions of 350 kilometers and 175 kilometers. Our boundary conditions are outflow with no inflow permitted. Our granite planets are collided with an impact velocity equal to 1.2 times the mutual escape velocity with an impact angle of 35 degrees. The target mass is 0.9 Earth masses and the impactor mass is 0.2 Earth masses. This particular set of initial conditions, as I previously alluded to, is called a hit and run giant impact scenario. It is known to produce a vapor-rich disk, again, bettering our assumption of ideal MHD. So we have to make a choice here. What are we going to do about including the magnetic fields? There are an infinite number of possibilities that you could choose for which magnetic field configuration you want to choose. But what we do is kind of motivated by the neutron star merger community. And that is, we seed each of our planets with a dipole magnetic field. And again, there's this question of how you want to orient these things. This is just another free parameter. But for this study today, we are going to consider the case where the dipole vectors of the target and planet are perpendicularly oriented. The magnetic field structure is computed by taking the numerical curl of a vector potential such that our initial conditions are divergence free. And we consider two different initial field strengths, which we define as the target and impactor poles. And these two magnetic field strengths are 10 to the minus 9 B crit and B crit. So now as I answer the question, well, what is B crit? Well, to accurately model MRI-driven turbulence, numerical simulations must resolve the most unstable mode of the MRI. In linear theory, the MRI has a maximum growth rate at a wavelength proportional to the alphane velocity divided by the Keplerian frequency. To resolve this fastest growing mode, this wavelength must be resolved by several zones. So we can say this a little bit differently, and this is this next equation. B crit is the field strength required to resolve the most unstable MRI wavelength in the protolunar disk midplane for a linear resolution given by delta x. Our two calculations serve a parameter space where the MRI could be resolved and where the MRI cannot be resolved. Well, you may be looking at these equations and saying, Patrick, this magnetic field strength is completely unfeasible. And I agree with you. For initial conditions, this is a very, very, very high magnetic field strength. But this magnetic field strength is what is required from the numerics of this problem to accurately be able to model MRI-driven turbulence. So what is interesting is if we had all the computer power in the world and we could really push down delta x to a really small scale, and if we could integrate these things on for long enough, then we could start with a much lower initial magnetic field strength and ultimately be able to enter this regime where the MRI is resolved. But for this first set of models at these given linear resolutions, this is what is required for our work. All right, so
Patrick, is 10 to the minus 9 chosen because that's thought to be an actually realistic? Like, why is that the number that you choose for your one other magnetic field strength?
So I chose that number because I want to be sure that the MRI is not resolved. And I wanted to be so small that I should see similar result, very, very similar results between a pure hydro run in a pure ideal MHD, or with an ideal MHD run with that low field strength. Okay, so this is a 3D visualization from one of our magnetized moon-forming giant impact simulations. And this visualization was made by an excellent undergraduate student that worked with Charles's group during the summer. His name is Evan Papoutsis. Here, color denotes logarithm of density, and white lines represent streamlines of the magnetic field. This animation takes us through the initial conditions, showing both the planet and impactor with perpendicularly oriented dipole magnetic fields. And next, we track the first hour of the impact. Recall, this is a hit and run collision with a collision velocity of 1.2 times the mutual escape velocity at an impact angle of 35 degrees. Upon impact, shocks propagates throughout the Earth. A tidal arm of debris forms. In the final state, we again show streamlines of the magnetic field. Clearly, magnetic field lines are stretched and wound by the impact. We do see some remnants of the dipole structure in the interior of the proto-Earth and in the tidal arm of debris. But making these 3D visualizations is very, very, very difficult and very, very expensive. And even though Evan did a completely incredible job, moving forward in my presentation, it is easiest to present slices through this animation through the collision midplane. And that is what I'll be showing from henceforth. So this animation tracks the log of the density and the collision midplane for the 175 kilometer linear resolution calculation with an initial field strength of B crit. And for this particular animation, I'm going to show you the first 48 hours of impact in contrast to only the first hour in the previous animation. So again, upon impact, two shocks form in the contact surface. One propagates to the proto-Earth and the other propagates to the impactor. As the initial encounter finishes, the proto-Earth is in a transient, distorted state. An impactor and target-derived materials form a tidal arm of debris. The impact launches a wave around the surface of the proto-Earth. Fields are amplified as magnetic field lines are stretched and wound by this wave and tidal arm of debris. Bound debris falls back to the proto-Earth and wraps around it, adding mass to the early protolunar disk. About 24 hours after initial contact, the debris has settled into the disk. The wave of material launched by the impact continues to propagate around the surface of the proto-Earth with about a 4-hour period. This wave drives spiral shocks into the protolunar disk. And by 48 hours post-impact, the magnetic field is strongest where the shear rate is largest. And that just so happens at the interface of the Earth and the innermost regions of the protolunar disk. Their plasma beta, or the gas pressure divided by the magnetic pressure, is of the order 600. In the disk midplane, field strength declines with increasing radius, reaching a beta of about 4,000. Yes?
Are we seeing all of the material that's gravitationally bound here, or is there some gravitationally bound stuff still floating at somewhat larger distances?
Yeah, so I slipped something under the rug.
Yes.
That is,
Where's the moon?
well, actually, that's not what I've quite slipped under the rug. The thing that I slipped under the rug is, why is this thing called a hit and run giant impact? Okay, so if you work it out, you'll find that the impact angular momentum for this particular model is larger than the angular momentum of the current Earth Moon system. And that is because in these particular models, some of the impactor actually escapes the system. So this is what is called the runner. And for these models, we allow the runner just to exit our simulation domain. So you are seeing all that is gravitationally bound, but you have to remember that this part of the runner has escaped our domain, which had outflow boundary conditions. But going back to your question is, you asked, where's the moon at?
Right, I mean, so then that's the stuff that eventually forms the moon much later on, as you said before. Yeah?
Exactly.
Yeah.
So in the very first video I showed you from Nakajima and Stevenson is this SPH model. And you could see that after their collision, you could see some clumps forming in their disk. I think something that is common for people to misinterpret is they think, oh, that clump right there, that's the moon. But that's not the case. The moon is thought to have formed, as the number I quoted for you earlier was Simon and Cannon found 1,000 years after evolution.
And that's sort of generic to all types of simulations, that you essentially destroy everything and then reconstruct the moon from the disk material.
Correct.
How much mass is in this disk? How many lunar masses are here?
This particular model has a disk about 3 lunar masses. Okay. So these models go on for a while. I only showed you 48 hours of evolution. But now they, as I said, these are the longest integrations that I'm aware of, and they go out to about 10 days post-impact. Beyond 120 hours post-impact, turbulence fueled by the collision itself has mostly dissipated, leaving behind a magnetized, differentially rotating protolunar disk. The top left panel here shows the magnetic field configuration at about 148 hours post-impact, and this is superimposed on the density field, log of density. We find that the natural outcome of a magnetized moon-forming giant impact is a disk that hosts a dominantly toroidal magnetic field. So moving forward, turbulence generated by the collision and magnetic winding have lowered plasma beta significantly by this time. At last, by 174 hours post-impact, the MRI begins to develop in the disk. And the top right panel here, you can see that magnetic field lines start to snake at angles of 45 degrees to lines of constant radius. And at 190 hours, non-toroidal components of the field are comparable to the toroidal components. The field is disordered. And by 220 hours post-impact, the remainder of the protolunar disk is engulfed by MRI-driven turbulence. So it's cool to see the onset of the MRI visually, but we can also study it quantitatively. We expect the components of the magnetic energy in the protolunar disk to grow exponentially upon MRI onset, with a growth rate of gamma equals 2 gamma max, where here this factor 2 just comes from the fact that we're looking at magnetic energy, which is field strength squared. The B naught equals 10 to the minus 9 B crit calculations should not exhibit an exponential phase, as the MRI is not resolved. So this figure shows the integrated magnetic energy associated with 3 components of the field: the toroidal, radial, and vertical field. For the B crit and 10 to the minus 9 B crit models, this integration of magnetic energy is done from about 2 to 3 Earth radii, focused in again on the midplane of the disk. As anticipated, the 10 to the minus 9 B crit run exhibits no detectable exponential growth. The radial and the vertical components of the magnetic energy remain roughly constant, and only the toroidal field grows, which is presumably due to magnetic winding of radial field. On the other hand, the B crit models do exhibit a exponential phase with the expected growth rates. We see that all 3 components of the field do grow exponentially. Okay, so what are the implications for the origin of the moon? So the top 2 panels of this slide show the vorticity in the protolunar disk for the 2 initial field strengths surveyed. For the very weak field case, the MRI, again, remember, is not resolved, and the disk is seemingly laminar in this plot. In contrast, for the B crit case, the vorticity exceeds the local orbital frequency by as much as an order of magnitude. MHT turbulence governs the evolution of the protolunar disk with a Shakura-Sunyaev dimensionless measure of angular momentum transport that we measure from our simulations to be about 10 to the minus 2. So disk turbulence leads to angular momentum transports. Now remember, I've alluded to earlier that the moon can only form when disk material is transported radially outward beyond the Roche radius, which for the Earth-Moon system is about 3 Earth radii. In the classical scenario for the formation of the moon, disk spreading is mediated by gravitational instabilities, and the associated spreading timescale is long, on the order of hundreds of years. But now with the introduction of magnetic fields, the disk spreading timescale is reduced to be of the order of 100 hours. So magnetic fields, in a way, could provide a way to hasten the formation of the moon. But there's another side to the story. Angular momentum transport sources accretion of disk material onto the proto-Earth. It is possible that magnetic fields may deplete the disk of some mass, therefore making moon formation less efficient. So let's revisit the questions that I asked at the beginning. What is the outcome of a magnetized moon-forming giant impact? We find that the outcome of a giant impact the outcome of a magnetized giant impact is a debris disk whose evolution is governed by MHD turbulence. And could a weak field be amplified to dynamical importance in the protolunar disk? Well, the answer is seemingly yes, The field is amplified by a combination of turbulence generated by the collision, magnetic winding, and the MRI. This is with the huge caveat that in these models, we are not considering finite resistivity, and we had a wonking large magnetic field strength to see these calculations. And finally, what are the implications of magnetic fields in the formation of the moon? Well, we found that the disk becomes largely turbulent due to the MRI, and thereby magnetic fields can make moon formation less efficient as materials accreted onto the proto-Earth. And secondly, magnetic fields can hasten the formation of the moon because remember, as we want to transport material outside the Roche radius, magnetic field, the angular momentum transport made possible through MRI-driven turbulence can make this time scale much shorter. All right, well, I had a whole nother part of the talk, which was going to talk about going back to this question of mixing to explain these isotope measurements. But given the time, I think that it would not be in my best interest to do that. So I was told to get it back. What's that?
5 minutes, could you do some, the major results, or
I can try.
go to the,
We're gonna have 10 minutes.
sorry?
Yeah, we have 10 minutes.
We've had a lot of questions during the talk, so we can keep those going, and maybe we just won't leave a 10-minute question period at the end. Okay, is that okay?
Sure.
Okay, so before I want to talk about mixing, let's bring it all together. As we have shown, the protolunar disk is differentially rotating and can be magnetized, which gives it the necessary ingredients for magnetohydrodynamics stability. With an MRI out, sorry, was there a question?
Oh, just so fast.
Oh, sorry, I can slow down.
I can't parse it.
Yeah, don't rush.
Okay, so we described that the MRI drives angular momentum transport, and the spreading time scale was roughly 60 hours. But one thing that I want to loop back to is that there's one missing piece to the puzzle. And I've added it here. It is the Earth protolunar disk boundary layer. The Earth disk boundary layer is the region where there's an abrupt change from the rotational profile of the Earth to the rotational profile of the Keplerian disk. The shear in this boundary layer region is larger than anywhere else in the disk, and it is supersonic. The boundary layer is dynamically interesting for a few reasons. First, although I argued that the magnetorotational instability will deplete the protolunar disk of mass, material simply cannot just fall onto Earth. Instead, it must pass through this transition region, the boundary layer. But inside the boundary layer, the MRI is not active. One recalls that the MRI requires an outwardly decreasing angular velocity profile. But inside the boundary layer, there is a sharp increase of this profile. So there's been a lot of work that has been put into looking at how material is actually transitions through this last region, this boundary layer. And actually, Roman, who is on the talk right now, is the expert in the field on looking at accretion through these boundary layers. And the thought is that there are these instabilities that arise due to the supersonic shear at the boundary layer that manifest themselves in the radiation of acoustic waves into the disk, sourced by the supersonic shear. So understanding how angular momentum transport in the boundary layer interacts with the MRI is essential to understanding how much mass can be removed from the protolunar disk. But also, this process will be interesting for mixing. Remember, we want to go back to the isotope plot. How can we explain mixing in these models? Well, the boundary layer is the location where disk material interacts with Earth-derived material. So it is in this region where we can pull material from the Earth into the disk to try and help mix material such that we can explain these isotopic measurements. All right, so the questions I want to ask for this segment are supersonic shear instabilities active at the Earth protolunar disk boundary layer? Second, does the boundary layer influence mixing between Earth and disk-derived material? And with this picture of the MRI and these supersonic shear instabilities at the boundary layer, how do magnetic fields influence mixing? All right, well, I guess the short result, which I will show you before I conclude, is that we developed, again, models using Athena++, where we use the equation of state modeling liquid and vaporized rock. And we look at this Earth disk boundary layer. The protolunar disk in these models is taken to be Keplerian, and we assume that it is in vertical hydrostatic equilibrium with a mass of approximately 3 lunar masses. Even though the initial conditions are described such that these are in vertical hydrostatic equilibrium, for this preliminary study, we restrict our models to 2D. That is, we initialize a 2D cylindrical mesh with our Earth and protolunar disk equilibria at the midplane. So we can approximate rotating Earth midplane in equilibrium by assigning a uniform angular frequency of Earth's solid body rotation, and then we assume a Keplerian rotational profile for the disk. So as a proxy for mixing, we evolve passive scalar equations, which track Earth-derived material and disk-derived material. Here in the equation at the bottom right, Ci corresponds to mass fractions of the different material reservoirs, where here blue corresponds to material derived from the Earth, and red corresponds to material derived from the disk. In order to investigate the role of solid body rotation in the post-impact Earth, we survey the non-rotating case with a rotational period of infinity, and the rotating case where the planet is rotating with a rate of a period of 4 hours. So again, for these models, we also have a bunch of free parameters. Another one is the thermal structure of the Earth and disk. We investigate the role of entropy of the Earth and protolunar disk in such that we assume that the Earth is isentropic and the disk is isentropic, but these entropies can vary between our models. And to see the supersonic shear instability, we add random noise to the radial and azimuthal velocities in the protolunar disk. All right, well, let me show you the video, and this one might make you a little bit dizzy. So this video tracks the passive scalar concentration corresponding to Earth-derived material for the first 240 hours of an Earth disk boundary layer simulation, where both the Earth and disk are assigned an entropy S+, which is the 6 × 10⁷ in CGS units. And the cylindrical domain is resolved by 512 radial zones and 512 azimuthal zones. In the initial condition, the passive scalar is set to 1 inside the Earth and 0 inside the disk. For this particular model, the velocity profile is discontinuous at the Earth-disk interface, and the Mach number of the shear layer is about 10. So the supersonic boundary layer of finite width is unstable to shear acoustic instabilities with a growth rate proportional to the Keplerian frequency, multiplying the radius of the planet divided by the width of the boundary layer. And after evolving our initial condition for 20 hours, the initially discontinuous velocity profile has broadened to give a boundary layer width of about 1/4 of an Earth radius. And at the boundary layer, the orbital period is about 4 hours. All right, at around 30 hours in this particular simulation, the supersonic shear instability begins to develop in the boundary layer. And the parent's m=7 mode is sourced at the boundary layer, instantiating mixing of Earth-derived material into the disk. At 40 to 50 hours, mixing is at its most vigorous, and the passive scalar concentration has reached a value of 0.4 in some regions of the boundary layer. Also at this time, angular momentum transport generated by acoustic waves yield the peak mass accretion flux onto the Earth observed throughout the duration of the simulation. By 240 hours, the density just outside the boundary layer has dropped by 5 times. The equilibrium, 5 times the equilibrium initial condition values. And at this point, the amplitudes of the acoustic waves sourced by the boundary layer have been substantially decreased. So this particular numerical model is an exemplary case for mixing in the protolunar disk. However, is not too realistic. This entropy that we used for this particular model in the previous slide was incredibly large and much larger than what we would expect from a giant impact simulation, unless we had a very, very, very highly energetic, high angular momentum model. But it's one of the only models where we were able to actually identify mixing due to these supersonic shear instabilities. So this particular, yes.
Maybe finish first on that.
Okay. So this plot shows you exactly that. For many of these models, including the ones that actually use an entropy more motivated for what we would expect the entropy of the post-impact remnant to be, show no mixing at all due to these supersonic shear instabilities. And only for these unfeasibly large entropies do we actually see mixing. All right, and with that, I think I'll just go ahead and jump to my conclusions. And yes.
Okay, very nice. What about the mixing due to the impact? Because there it looked like you're basically liberating a large part of the Earth. Because here you were just tracking what happens after the collision has already happened. But how do you distinguish the material that comes due to the boundary layer interaction from the one you see?
Great question. So remember for these models that for the canonical joint impact hypothesis, they did look at scalar evolution and found that the final disk that forms is largely comprised of impactor derived material. So you need a way of getting material out of the Earth into the disk in order to equilibrate these isotopic signatures.
And that is generic independent of the impact parameter and the angular momentum.
That is dependent on, you get more mixing with higher angular momentum impacts.
Okay.
For example, there's this recent model where you have a head-on impact at a very high angular momentum, and is thought to produce this structure which has been named a synestia. It's been given its own name, and these models are supposed to completely mix the material such that you don't even have to worry about this post-impact equilibration. But the idea here is that even though I've looked at mixing between Earth and disk-derived material, you could use as initial conditions for this model what fraction from the impact corresponds to impactor-derived material and Earth-derived material. But the major result of this study that I think is that even with this simple prescription, we find that mixing is very, very inefficient at the boundary layer due to these supersonic shear instabilities. So no matter what happens in the impact, this seems as not a likely way of fixing that problem. All right, so on that note, are supersonic shear instabilities active at the Earth protolunar disk boundary layer? Well, the answer is yes. All models do show evidence for the excitation of acoustic waves at the Earth protolunar disk boundary layer, and acoustic waves do promote mass accretion onto the Earth. But the question that might be more interesting for the formation of the moon is, do they influence mixing? Well, inefficiently. In our preliminary simulations, mixing is only observed in cases where Earth is initialized with a very, very, very high entropy rotating equilibrium. All right, and finally, something again that I swept under the rug in the interest of time is, how do magnetic fields enter the mix? And that is in these high entry models, we do produce some mixing at the Earth disk boundary layer, but this material is restricted to be inside a certain radius. We need some mechanism in order to transport this material beyond, this mixed material beyond the Roche radius so that it be incorporated to the formation of the moon. One possible way of doing that is including magnetized turbulence, which can take this material and transport it radially outwards. Also, in our models, we found that the supersonic shear instabilities effectively turned off as soon as enough mass was depleted from the inner disk onto the Earth. If we have magnetic fields, then there will be a constant supply of mass into the boundary layer due to mass accretion from magnetized turbulence. And maybe this could promote longer mixing times, which might change the picture. But I think the general idea right now is that it probably won't solve the isotope crisis. Thank you.
So I have one more question about like super long-term evolution after all of this has happened. So one of the really surprising things to me is you said that the disk is three lunar masses, and then you accrete actually some of it onto Earth. So whatever, moon must form very efficiently, right? So that's surprise number one. Then the other question I have is, whatever remnant of the disk is left between the moon and so after the stuff has moved beyond the Roche point and formed, there will be some stuff that will have cooled. At that point it's just like kind of pebbles, right? So what happens to that, and on what time scale does that clear up?
Okay, so the first question was about efficiency. So one thing that I'll say is that if MRI turbulence is active in the protolunar disk, like you said, mass will be accreted onto the Earth, thereby depleting the mass budget available to form the moon. In one sense, that is a bad thing, because magnetic fields may not be possible, or MRI turbulence may not be possible because it just depletes the disk of so much mass that we can never form the moon. But on the flip side of that is maybe the incorporation of magnetic fields allows for us to consider impacts that produce much more massive disks, because we need to be able to, if we're going to be accreting so much mass onto the Earth, then we need enough left over. So maybe that could look at different impact scenarios. Second question was timescales. So first, I'll say that yes, you're absolutely right. In this magnetized picture, what we think will happen is that the disk will, so as we have this alpha of 10 to the -2 from the MRI, the disk will radially spread outwards, and in doing so, it will adiabatically cool. And we think that effective cooling of material and condensing of solids can only happen once this material can escape the influence of the MRI, which will only happen when the flow decouples from the magnetic fields. And there are some estimates from that in Gamma record 2016. They find that this decoupling radius is about 10 Earth radii. And then only after this material decouples at this ring, at this large radius, can we actually start condensing to form the moon. And that will happen on timescales associated with the gravitational instability.
Any more questions? Any people from Zoom? Yes.
Roman speaking. So these are amazing simulations. I mean, it's quite spectacular to see the MRI grow after an entire giant impact calculation like that. My question is that you see the growth of the MRI suddenly appearing after 120 hours, if I'm not mistaken. Is this because the field is growing because of the winding, and suddenly you reach the resolution to see the MRI?
Yeah, that's exactly correct. So I quoted this number to you about B crits being of the order of a kilogauss, but that is defined at the target and impactor poles. It is not representative of the magnetic field strength in the post-impact remnant. So in fact, field strength that we actually observe inside the post-impact remnant at about 3 Earth radii, I think is more on the lines of 100 Gauss. There we are not resolving the most unstable MRI modes. So we need to give some time for magnetic winding to grow, to wind radio field linearly in time until we can actually see this thing ignite and the MRI turbulence carry off. So you can also ask the question, what would happen if I start with even lower field strength? And we've actually done this run, this calculation, and we found that pretty much what happens is that you just delay this exponential growth phase, depending on how much time it takes for winding to grow field strength enough such that you're resolving these fastest growing MRI modes.
And so have you considered also running simulations with a constant field that could be, you know, the scenario where the field is more the interplanetary field instead of the initial dipolar field of the two impactors?
You mean just like an initially vertical field or something like that?
Yes, so I mean, I don't know, maybe qualitatively it doesn't change much. But you know, you mentioned at the beginning of your talk that you have two hypotheses. One is that you have dipolar field in each, you know, impactors, or that you have just the magnetic field of the sun, which, you know, is pervasive in the Earth region. So I'm just wondering whether this would change qualitatively the picture, or it's just a minor detail in the setup.
Yes, so I agree. As I said earlier, there are infinite number of choices that what we can use for these initial magnetic field configurations. We just selected this one where they are perpendicularly oriented, but something that's kind of cool is that maybe we've encroached on this new field where we could just produce this phase space of magnetic field orientations and figure out which initial conditions actually promote MRI growth. You asked in particular about this vertical field. And I think that's a particularly interesting model because the MRI is most sensitive to the poloidal components. These axisymmetric disturbances are grow much faster than these non-axisymmetric disturbances. So maybe these vertical field models would promote MRI growth much more quickly than our models, which have a dominant toroidal components.
But in that case, would you have magnetic braking effect?
In which case, with a vertical field?
Vertical field, yeah, something similar to the protostellar disk.
I'm not sure. I think that physics is not included inside of our models, so we would require a big overhaul.
I don't see Any other questions? So let's thank Patrick again. Thank you. And